Hello everyone, my name is Merangoli, and today I'm going to present our paper entitled ASCHyRO Automatic Fault Localization of SystemC HLS Design using a Hybrid Accurate Rank Ordering Techniques in ICCD 2020 conference. The increasing functionality of digital systems and reduced time to market constraints push designers to model systems at a higher levels of abstraction than the traditional register transfer level RTL. Hence, high-level synthesis at the electronic system level is being increasingly adopted by the semiconductor industry to boost the design productivity. HLS designs are typically developed using SystemC language as a de facto standard at the ESL and can be automatically synthesized into RTL. This means that HLS designs are reference model for lower levels of abstraction. Thus, their verification is of utmost importance as undetected fault may propagate to lower levels of abstraction and become very costly to be fixed. Although lots of progress has been made in terms of correctness assurance of SystemC designs, providing an automated debugging solution has received less attention, mainly due to its object-oriented nature and the complex language construct and semantics. In general, the debugging process consists of two main steps, which are fault localization, meaning the identification of possible faulty locations that eventually lead to design failures, and fault correction, which means locally modifying the functionality of the identified portions. The fault localization is considered as the most time-consuming step in the debugging process, and its quality affects the fault correction step. In this work, we focus on the fault localization of SystemC HLS designs that is the critical step of the debugging process and typically takes a significant amount of time and effort from designers. In this slide, we explain challenges of fault localization in SystemC HLS designs using a motivating example. Consider the two-stage pipe design implemented in SystemC. The design includes two modules M1 and M2 and performs a set of algebraic operations to generate the final results in two steps. Here, we also assume that the only reference that is available for designers is the correct value of final outputs as a reference result. Now, consider the scenario that designers made two mistakes when implementing the design. First, an incorrect assignment where the definition of variable gen_b is incorrectly implemented. Second, an incorrect operator where the local variable temp2 is incorrectly defined. After executing the design, they found that the value of final outputs out1 and out2 of module M2 is incorrect. Therefore, an important task is now debugging, which means localization of the faults and then fixing them. However, fault localization of SystemC designs is very challenging, as the C++ compiler cannot detect these types of faults as they are functional faults and are not related to the C++ or SystemC syntax. Monitoring the simulation behavior of the design is very time-consuming as it requires to manually trace runtime values of all design's variables. Therefore, it does not reduce the number of fault candidates and the search space. Since no reference model or a basic specification of the motivating example is at hand, the formal methods are not applicable. Moreover, as SystemC lacks formal semantics, translating SystemC source code into a formal language is not a trivial task. The existing C-based debugger methods are not applicable as they do not support SystemC construct, data types, and semantics. And finally, simulation-based method at the ESL focusing on visualization and monitoring of the design behavior and not fault localization. Our proposed methodology, ASCHyRO, to address this problem consists of two main phases, which are hybrid program slicing and ranking analysis. Before going to the details of the approach, we need to know what is the program slicing. The program slicing technique has been introduced for the first time in the software domains to identify parts of a program which have an impact on a selected set of variables. Parts of the program that do not affect these variables are eliminated and hence a reduced set is obtained. This reduced variable set is called a slice. To perform program slicing, we first need to translate the design into a set of formal representation. We consider two data structures which are correlation graph and homograph. The correlation graph describes how different variables of the design are related to each other, and the homograph specifies how different statements of the design are related to each other. These are done by analyzing the abstract syntax tree of the design using Clang compiler. After generating these data structures, we perform program slicing, where static slicing is performed on correlation graph to identify the dependency of a given output to the designed variables, and dynamic slicing is performed on homograph to identify those variables and lines of code that associate to the faulty output for a specific input test. In the second phase, results of the static and dynamic slicing are combined to create confidence score for each variable of the designs and a reduced set of lines of code. The confidence score is calculated based on two parameters, which are the probability of fault occurrence on a variable derived from the static and dynamic slicing. The first step of performing the program slicing is to extract the correlation graph from the abstract syntax tree of the design. Once the correlation graph is extracted based on the cones of faulty outputs, the correlation graph is sliced into some regions. In the case of the motivating example, 7 regions are created. The identified regions in a correlation graph are completely independent from each other, and each node of the graph is only a member of one of the regions. For example, regions R1 only includes nodes of correlation graph that belongs to cone out 1. In the second step, the homograph representation of the design is extracted by analyzing the abstract syntax tree of the design. The static slicing of the homograph for a set of faulty outputs is performed by identifying all nodes of the graph on which the outputs are dependent. A node in the homograph is considered as a dependent node to a given output if the corresponding statement of this node has at least one variable that is located in the cone of the output. Black circles in this figure show statements that influence out1 and out2, while white circles show statements that do not have any impact on them. The executed statements are obtained by running the program with the input test that cause faulty outputs. The dynamic slicing is performed by finding the intersection of the static slice of a homograph and the executed statement. The ranking analysis is performed to calculate a confidence score for each variable of the design and consequently a reduced set of lines of code. The confidence score is calculated in 2 steps, static and dynamic ranking. The goal of a static ranking is to specify the exact fault occurrence probability on nodes of correlation graph. To do this, we calculate the probability of fault occurrence for each region combination and subsequently calculate the probability of fault occurrence on each node of the selected region. To improve the confidence score of each variable, a similar probability analysis is performed on the region representation, including nodes that are obtained from dynamic slicing results. In our motivating example, after performing dynamic slicing, node N9 is eliminated from R1 as its corresponding statement was not appeared in the execution time. The probability of fault occurrence for each node is added to the confidence score of its corresponding variables. By this, we have 4 classes of variable candidates where the actual faults are in the first 2 classes, including 5 variables. In this slide, we show the results of applying ASCHyRO to different types of SystemC designs for localizing single fault and multiple faults. As can be seen in this table, in case of single fault, ASCHyRO on average reduces the search space by 82% in terms of line of code and 78% in terms of the number of candidate variables. In case of multiple faults, 76% in terms of lines of code and 71% in terms of the number of candidate variables reduction were achieved. The best case reduction results are related to the packet switch, RISC CPU, and LZW encoder benchmarks, where up to 96% reduction in search space was achieved. In comparison to the pure compilation and execution time of each design, the execution time of ASCHyRO is in the same range, that on average it takes 20 and 22 seconds to localize single fault and multiple faults respectively. As a conclusion, we introduced the first SystemC HLS fault localization approach at the ESL. ASCHyRO takes advantage of semi-formal techniques to provide designers with a reduced order of potential fault candidates. We target the common modeling mistake affecting the functionality of SystemC designs, such as fault state transitions, incorrect assignment, and incorrect operator. And finally, experimental results show the effectiveness of our approach in localizing even multiple faults with a high confidence in a short execution time. Thank you for your attention and have a nice day.